So we continue here with Kaufman, and I really hope the wind is going to side for a while here, so I can make my recording in peace and quiet. Well, I believe that it is a fundamental insight that the universe is identical with self, that it should be possible to reformulate present-day physics so that it is seen as a form of the living. We are not there yet, but Fields et al. Have gone forward with the courage to explore aspects of this possibility for unity. Now we go over to Konrad Werner, another critics of the aforementioned article that I started with 2 lectures ago in 1208. Certain questions regarding perceptions and boundaries. Konrad Werner at the University of Warsaw. Upshot. I elaborated how boundaries are accounted for in the target article. This is a substantial issue if we are to understand the proposal laid out by Fields et al. I argue that certain boundary-related notions and theses need clarification. 1. Perception has to do with boundaries. I find this general idea laid out in the target article by Chris Fields et al. Very intriguing. The text is insightful in many respects, yet it is also dense, which makes addressing all the issues that should be addressed virtually impossible. For that reason, I shall focus solely on the problem of boundaries. They are salient factors in the proposal under consideration. However, certain things need clarification. There is a literature on boundaries, in particular a subdiscipline of ontology called mereotopology. I shall not refer to this literature, though, as it would require much more space. 2. So what does perception have to do with boundaries? The authors say that the perceived world, the familiar realm of the things that we perceive every day, results from an encoding from incoming data first, and that this happens on the boundary that separates us from our surroundings. However, crucially, the perceived spectacle does not encode information about the ontological or causal structure of the world. It is rather information about the structure of the finite fitness function that relates the agent to the world. Paragraph 3. This means that the outside world is a black box. a metaphor brought up by the authors themselves many times, that is in a sense hidden. 3. How many boundaries? Imagine that you're on a beach and you see the line dividing the surface of the sea and the sky above. Now, how many boundaries are there, and to which entity do they belong? Is it the case that the water or the air is closed, meaning that it has its boundary as a part, while the air, respectively the water, is open? That is, it does not have a boundary of its own. Thus, the boundary of one entity serves as the boundary between the entities in question. Or is it the case that both the water and the air have their own boundaries, and that these boundaries abut each other? Finally, perhaps the water and the air share the boundary, meaning that the latter is a common part of both entities. These questions may seem silly, yet if being bounded is an essential feature of some entity, a condition of its identity, the issue becomes ontologically critical. When it comes to our case, the articles claims that perception is a spectacle played on the boundary between the perceiver and the outside world. But how many boundaries do we have there? Here is the first option. One BPV. There is one boundary. It belongs to the perceiver and to the outside world. It is shared by them. They are both closed. So we have a boundary between the perceiver and the outside world. This option is clearly endorsed by the authors in paragraph 10. 5. If we generalize what the authors say in paragraph 10, then the perceiver and the outside world are neither closed nor open. Originally, the model outline in the target article referred to the simplified situation in which an outside world for one perceiver is another perceiver. This cannot be right. The alleged purely notional character of the boundary in question has nothing to do with the context. This is because by deeming the boundary purely notional, we take a particular position as regards the nature of the boundary, not about its very existence. So, for example, the boundary between Poland and Russia, Kaliningrad Oblast, for instance, is purely conventional, but surely it exists, and it is even guarded by heavily armed forces. So if there is a boundary or boundaries between the perceiver and the outside world, regardless of its nature, the two realms must be either closed or open. 6. So suppose that we have one boundary shared by both sides, as the article proposes. This means that both the perceiver and the world are closed, yet they are not separated. Imagine two pieces of material sewn together. They are distinct and each of them is bounded, but they cannot be set apart. They are part of one whole, so to speak, precisely because they are sewn. However, there is one subtle puzzle here. If the perceiver and the world are sewn by their shared boundary, then one can hardly say that what happens in the sewing itself has nothing to do with the ontological structure of the world. After all, this sewing is likely part of the ontological structure. If not, then what is it? 7. In this context, we can notice an interesting tension in the very nature of at least some boundaries. Think of a living creature. Boundaries constitutes an organism by cutting off from its environment, yet at the same time, they provide channels for communication with the environment. Say, once they bound something, they open some doors to make traffic possible. When it comes to the philosophy of mind and perception, this tension is crucial. There is the Cartesian approach to the mind-world boundary, putting stress on isolation or separation, while, for instance, in Edmund Husserl's or Maurice Merleau-Ponty's approaches, the boundary in question was supposed to, let me use Husserl's original and very pregnant formulation, bring the world to a presentation. The authors apparently take the Cartesian route, and I'm not sure if that is necessary for the project as a whole. 8. But perhaps there are actually two boundaries, as it is also suggested in paragraph 10, where the authors introduce a distinction between a boundary and its surfaces. But is the surface not a boundary too? So we can at least take into consideration the following scenario, and this is 2b. There is one boundary that belongs to the perceiver and one boundary that belongs to the outside world. They are both closed. So here we have the perceiver and then we have the outside world, and the difference is total. It's complete isolation. However, this case is very problematic due to the fact that it becomes unclear where exactly the information is encoded, on which boundary does this process occur. If it occurs on the perceiver's boundary, then what role is left to be played by the world's boundary? Perhaps here is the point where the idea of the structure of fitness as opposed to the ontological structure of the world comes on stage. Suppose that the world's boundary provides a barrier that the perceiver bumps against, so to speak, adjusting its shape, that is, adjusting its boundary so they fit metaphorically to the world's boundaries. However, if there are two separate boundaries and their abutting determines the structure of fitness, then why is there any need for a rather complex process of encoding information and establishing this whole theater of phenomena that we face once we open our eyes in the morning? This is just another way of formulating what David Chalmers in 1995 once called the hard problem of consciousness. Yet, from a different side, this is, say, the hard problem of presentations. Why they present something rather than nothing. Why we are not zombies bumping against the boundary of the world, adjusting to it, and by doing so maintaining solely our structure of fitness. It seems that we could do so without facing any phenomena, and it's likely that the most primitive organisms still functions in this way. Perhaps stripping the perceiver from its boundary yields an even better understanding of the structure of fitness. So, then we try this one. The border is solely outside of us. It's in the outside world. And we call that one border world. The perceiver is open and the world is closed. Here, the perceiver is shaped by the boundaries of the world as boundless water poured into the glass. In this sense, the perceiver fits the boundary or boundaries of the world. This boundary must be there, pre-given and ready-made. And this is a term coming from Hilary Putnam, the grand philosopher of science. Independently of the perceiver, if the latter is supposed to adjust itself to it. Such an scenario has been discussed and criticized by, for instance, Francisco Varela, Evan Thompson, and Eleanor Roche. However, aside from Varela's criticism, Here, as in the border belongs to the person, perceiver scenario, it is not clear why the structure of fitness is distinct from the alleged ontological structure of the world. After all, the boundary that the perceiver faces partakes in this ontological structure. If it does not partake in it, then what is it? Thinking of the boundary in question as if it were like a mere wrapping paper, having nothing to do with the thing being wrapped. The world in this case makes the boundary a mysterious, superficial entity of unknown origin. But if it's not a mere wrapping paper, then one cannot say that the ontological structure is hidden behind the boundary. The structure is there, and the boundary is its manifestation. 10. Finally, there is a scenario that strips the world from its boundary. Which takes us to that there is only one border, and it's the perceiver that's close and the outside world is open. 1 BP, border perceiver. Berala et al. Likely have this scenario in their minds when they write that our lived world does not have predefined boundaries. Cognition, this is a sight, is not the representation of a pre-given world by a pre-given mind, but is rather the enactment of the world, and a mind on the basis of history of the variety of actions that the being in the world performs. Here, admittedly, we cannot speak of a pre-given or ready-made ontological structure of the world in the absence of what the perceiver does. However, whatever the structure of this world is, it cannot be regarded as obscured or hidden either. Here, structures of the world results from the perceiver's interaction with the world. To conclude this part, I wonder to what extent the conception outlined in the target article could be freed from the Cartesian idea of the world's being ready-made. It's having a structure independently of cognition and hidden because meaning the inaccessibility of this ready-made structure. So let's look at another variety. How many types of boundaries? The scenarios presented above, as well as those presented in the target article, suggest that there is just one place where the perceiver world boundary is drawn, so that both sides seem to be like two blocks. But what forces us to accept this two blocks model? Maybe it would be much better to draw several lines composing a more complex structure, say something like this. And here is a depiction of the perceiver being intermingled with the outside world, still pertaining to his or her borders, but in some cases it's more open than closed. Someone might say that there is no essential difference between the latter and the former scenarios. While this is correct, the latter drawing makes an important suggestion. Both sides, that is, the perceiver and the world, are shaped with respect to each other. The boundary line is not just a line, it contributes to what the two bounded realms are. There may be, however, an essential difference too. The essential yet rather tacit assumption behind what I have just dubbed provisionally the two blocks model is that there is just one type of perceiver world boundary. But why? Perhaps each perceptual subsystem, be it vision, hearing or touch, sets up and imposes the world its own structure of boundaries. Note, from the evolutionary perspective, the step from the mere mechanical senses like touch or from chemical senses, the oldest one, to vision, the step that marks a great evolutionary achievement, originated from a new ability to target what was literally on the boundary of an organism, where receptors are plugged in, not as the object perceived, but a signal of an object or as information. Hence, while in the case of touch, the boundary of the thing being perceived abuts the physical boundary of the perceiver. In the case of vision, for instance, these respective boundaries have nothing to do with each other. But perhaps, let me set this off as a speculative hypothesis. Together with vision, a specific new system of boundaries came into being, so that, say, the vision-determined boundary of the perceiver is not identical to its physical boundary qua organism. And at the same time, this new boundary serves as the vision-determined boundary of the thing perceived. Here, perception, cognition in general, brings forth significantly new types of boundaries, and this is a constructivist aspect of the idea. Impose these boundaries of the world so that the world is brought to presentation in such a guise, and perhaps further steps in this evolutionary process resulted in the boundaries of what we used to call mind. Recall Andy Clark and Schauman's groundbreaking idea of extended mind. What they propose boils down to the claim that the mind sets its special arrangements of boundaries that are not identical to the physical boundaries of the body. Very good. Konrad Werner, very interesting. Well, Konrad was quite interesting, and let's get back to him promptly, I think. Now we stride on to eigenforms, interfaces, and holographic encoding. Their relation to the information loss paradox for black holes and quantum gravity. Well, listen to that. Antonio Marciano at the Fudan University. Upshot. I emphasize possible analogies and links between the content of Fields et al., Al's target article, and some consolidated recent studies in the literature of quantum gravity and the information loss paradox for black holes. This follows from the attempt by the authors to account for space-time as an error-correcting code. The paradigm the authors focus on can be naturally cast in the language of some models of quantum gravity based on graph theory, and suggest a generalization of the perceptual systems so as to account for the quantum holographic encoding as described in quantum gravity. At the core of the target article, eigenforms, interfaces, and holographic encoding toward an evolutionary account of objects in space-time, there is the development of the interface theory of perception, made by Hoffman, Singh, and Prakash. This framework is unfolded within the very same language in which the epistemic foundations of quantum mechanics can be phrased. The interface theory of perception allows a detailed description of the holographic encoding and is naturally tailored in order to account for the communality of the observer environment interfaces interactions. Within this framework, the authors addresses the structure itself of space-time after having reviewed and analyzed the most relevant options for holographic encoding and summarized the propositions for the fitness functions deployed in the interface theory of perception. Although the axioms of quantum mechanics are not explicitly stated, the focus throughout the work is on quantum states, entanglement, and observer-environment decoherence. The underlying assumption is therefore that the theory of perception should be addressed and studied through the lenses of quantum mechanics. The authors explicitly mention criticism of the assumptions of epistemic transparency and objective persistence, proper of the classical worldview, and point toward the elaboration of experiences within the theoretical framework of quantum mechanics. They ascribe a particular relevance to unitary quantum theory as the correct paradigm in which to address decoherence and holographic encoding. As they point out, in unitary quantum theory, the universe is permanently in an entangled state. There are no classical objects. Besides the philosophical preference toward unitary quantum mechanics, the line of thought followed by the authors has a striking overlap with a vast part of the literature developed in the last 4 decades about the information loss paradox of black holes, and crosses its natural consequence, which is the development of the holographic principle. There are evident analogies that assimilate the crucial role of the black hole event horizon in the flow of information to the role of the membrane between observer and system in the interface theory of perception. The comprehension of the function of the physical degrees of freedom that puncture the observer's system interface represent a possible pathway to solve the information loss paradox. The key point is to overcome the no-hair theorem for classical black holes. This states that the thermodynamics of black holes shall be described only in terms of 3 quantities: the mass, the spin, and the electric charge of the black holes, all other classical degrees of freedom being irrelevant. The no-hair theorem can be avoided by resorting to the notion of quantum has. The latter are quantum numbers that black holes may carry. The latter are quantum numbers that black holes may carry, which are not associated with massless gauge fields, and which may solve the information paradox, allowing for storing of information. This is a perspective that comes from an old idea that recently underwent a particular revival in the literature of high-energy physics, thanks to the intuitions of Stephen Hawking and to the work of Hawking, Malcolm Perry, and Andrew Strominger on soft photons. The very quantum mechanical description of the theory of perception the authors move from can naturally encode quantum has. But then a first provocative question to address would be, can an observer have access to quantum hairs and thus to the information that can be encoded in these latter entities? Beyond this analogy between event horizon and interface of perception, it is possible to point out a more general correspondence between quantum degrees of freedom that are encoded on the observer system boundary and some theories of quantum gravity that make explicit use of graph theory. Among the latter, we mentioned loop quantum gravity from Ruelli, 2004, and theoretical constructions that arise from string nets, gauge interactions, and eventually also fundamental particles of the Standard model can be derived in these two frameworks. The basic objects of these theories are graphs, namely sets of nodes interconnected by links, which are colored by fundamental representations of some continuous or discrete Lie group. The latter are sets of elements on which it is possible to define a product rule, recover a unit element, and then find an inverse element that reproduces the unit element by virtue of the product rule. The redundancy that the authors propose to be deployed for unraveling the emergence of space and in general space-time as an error-correcting code could be then associated with the irreducible representations that are assigned to the links of the graphs of these theories. This is exactly the same construction developed in the loop quantum gravity or string nets. The quantum states of the models of emergent spacetime are then recovered from the graphs that are taken into account. The colors, which is the irreducible representations of elements of the Lie group, are now associated with eigenvalues of the observable quantum operators of the theory. The dimension of the Hilbert space associated with the irreducible representations of a discrete or continuous group, Lie group G, or eventually to a quantum group that are assigned to the links of the graphs is the natural instantiations of this line of thought and might represent redundancy. Moving from such an intuitive approach, we are led to ask a second relevant question. How can we encode the observer system duality in those models of quantum gravity that are phrased within the language of graphs? If we take into account the author's analysis in paragraph 15 to 17, it seems natural to argue that the individuation of an interface distinguishes two subsystems of the Hilbert space, and thus implies that the total set of degrees of freedom encloses both the observer that perceives and the perceived system. Nonetheless, redundancy would require, in order to let emerge the notion of space-time that satisfy the Einstein equivalence principle. That a continuous group structure G could be consistently defined for the spaces of actions, and that this G could be connected to the Lorentz group. As the author points out in paragraph 33, a sizable amount of energy expenditure is required for the holographic encoding, which is roughly proportional to the number of bits involved at the interface and to thermal energy for each degree of freedom. This implies that the redundancy increases in proportion to the dimension of the Hilbert space at the boundary between the observer and the system. Thus, the simple system described by a binary chord, namely the Hilbert space of spin, half particle in the physicist jargon, might already turn into an extremely complicated model to be solved. Nonetheless, at least from a theoretical perspective, we may ask what happens if the Hilbert space at the boundary is composed by n degrees of freedom whose internal degeneracy is described by the irreducible representation of a Lie group G. The main last question I propose is therefore, what is the nature of these degrees of freedom at the interface between the observer and the system, and what is the internal degeneracy group, namely the redundancy connected to these degrees of freedom. The answer to question 3 amounts to the correct reconstruction of the boundary physical theory. We must indeed recover the relevant degrees of freedom at the interface and consistently describe at the quantum gravitational level the interactions these undergo, the role of symmetries to which are connected, charges that may play the role of bits is indeed very intertwined with this aspect, as emphasized in a series of studies by Hawking, Perry and Strominger. I wish also to emphasize that the role of quantum gravity is not only crucial to determine the dimensionality of the boundary Hilbert space. This pertains to the total set constituted by the observer and the system, and accounts for the description of their interaction, but is relevant as well to regularize the maximum amount of degrees of freedom that shall be considered while reckoning the exchange of bits and the flow of information through the membrane. This provides a setup in which we can operationally accomplish circulations, avoiding infinities. I end this brief commentary by recalling the author's suggestive remark. Part of common belief in the community of quantum gravity that has been growing in recent years, that with the relation between interfaces perception and holographic encoding, we may only actually be probing the tip of an iceberg. A deeper understanding of the emergent nature of space-time might indeed arise from the development of a theory of quantum information, gravity, that many authors are currently developing in the literature. So, those were all the rebuttals to Chris Fields et al.'s article. Now I will go into the author's response, and we start with Chris Fields. No, it's all of them. They've written the response together. All the better. Author's response: boundaries, encodings, and paradox. what models can tell us about experience. Formal models lead beyond ordinary experience to abstractions such as black holes and quantum entanglement. Applying such models to experience itself makes it seem unfamiliar, even paradoxical. We suggest, however, that doing so also leads to insights. It shows, in particular, that the view from nowhere implied with the theorist is both essential and deeply paradoxical, and it suggests that experience has an unrecorded, non-reportable component in addition to its remembered, reportable component. We thank our commentators for their insightful criticism. While each of them chooses a different focus for their comments, the issue they raise overlap considerably. We highlight in what follows what we take to be the major issues and attempt to show how they relate both to what we propose in the target article and to one another. The classical world is the explanandum. Constructivists, phenomenologists, and others who reject naive realism are faced with the task of explaining a shareable experience of the classical world. A world of tables, chairs, dogs, cats, and people. Even the naturalized sciences, however, face this challenge. This is obvious in the case of quantum theory, but even the classical theory of atom-based matter, the classical physics of the late 19th century, faces the problem of how clouds of atoms could appear to us to be tables or chairs. It is less obvious in the case of biology and psychology, but here it must be explained how agglomerations of cells, i.e. organisms, could self-assemble in ways that allow the experience of such things as tables and chairs, as opposed to, say, just brightness and saltiness. We agree with Dietrich that the experience of the classical world is ineluctable. When we open our eyes, we see bounded objects with definite shapes, sizes, and locations. When we open our ears, we hear tones with definite loudness and pitch. When we open our eyes, we see bounded objects with definite shapes, sizes, and locations. When we open our ears, we hear tones with definite loudness and pitch. Our goal is to explain why we have such experiences. Dietrich suggests that the experience of a classical world is ineluctable because there is an ontologically real classical world. One with a mind-independent space-time that is filled with mind-independent objects. We visit this world by opening our eyes and ears. According to Dietrich, an utterly different structured quantum world that we can access only via our thoughts can be considered to be equally real. And there might be other equally real worlds with yet different structures that we cannot access at this time. From a constructivist perspective, these worlds are all constructs, one of our perceptual systems and the others of our theoretical imaginations. Why the former should provide compelling experimental evidence for the latter remains a mystery. Why can we only express our theories, even to ourselves, in thoughts, using classical symbols, is also mysterious. Give me a second here, I need to... Why the former should provide compelling experimental evidence for the latter remains a mystery. Why we can only express our theories, even to ourselves, in thoughts, using classical symbols, is also mysterious. We attempt to address these questions by appealing to a specific mechanism, the holographic encoding of an interface that employs space-time as an error-correcting code. We each see a classical world in our view because we each have this kind of interface. The objects, including objects of thought, that our interfaces present to us are eigenforms. As Heinz von Förster emphasized, eigenforms and the corresponding eigenbehaviors are, at least approximate, fixed points of multiple, repeated, ideally infinitely repeated perception action loops. Eigenform and eigenbehavior must be classically correlated across these repetitions. Hence, the process of repetition, whether it is conscious or not, constitutes a memory. It is this memory of classical correlation that confers classicality on the classical world, our interface encoded experience. If we are correct The classical world is not a world at all, but it is only an experience. The classical world experience is ineluctable because the interface that encodes it is the only interface we have. As Ernst von Glasefield puts it, summarizing 3 millennia of philosophical empiricism, it is impossible to compare our image of reality with the reality outside. When we imaginatively construct theories of what lies beyond the interface, we construct and express them using symbols and diagrams that our interfaces allow. Classical symbols and diagrams that have definite arrangements and shapes. Such symbols and diagrams are, like our percepts, eigenforms. Fixed points that are only recognizable through repeated use. We have no choice in our use of classical symbols and diagrams, as our experiences of theory construction and our experiences of our constructed theories are experiences of our constructed theories, our experience, and so are encoded on our interfaces. The classical symbols and diagrams that we use to express our theories make us use redundancy in space and time. Hence, they enable error correction. What we have called the classical worldview, on the other hand, is an assumption that the classical world of our experiences is not just encoded on our interfaces, but also exists beyond them as ontologically real structure, comprising a multitude of well-defined, bounded, time-persistent, macroscopic objects. We see tables and chairs in this worldview because tables and chairs, not just clouds of atoms, are out there, bouncing light into our eyes. Perception is mostly veridical because the interfaces through which we have perceptual experiences are mostly transparent. The world on this worldview is not a black box at all, but rather a mostly white one. What you can see is what you get. Dietrich argues that this worldview distinction is illegitimate without empirical evidence that our model is correct. We disagree. The classical worldview is an explicit philosophical claim, or more commonly, an implicit and perhaps innate assumption that can be, and in point of fact is, made independently of whether the classical world that it postulates actually has the ontological status that the classical worldview claims it to have. On the other hand, we agree with Dietrich that there is a deep issue here. Stating the distinction is making a statement. and making any particular statement is a classical act. If the classical worldview is rejected, the status of statements is cast into doubt. It is unclear how anyone could speak one particular sentence or think one particular thought. Memory and communication both become paradoxical. Any non-classical theory seems to require, as Niels Bohr argued, a classical meta-theory just to support language. Here, a dialectic world seems inescapable. While we do not, as Dietrich points out, have direct empirical evidence for our model, there is plentiful, albeit indirect, evidence for holography as a mechanism. Many would argue, moreover, that the mounting evidence for quantum effects at macroscopical scales demonstrates empirically that the classical worldview is wrong. As Dietrich emphasizes, accepting this argument requires the acceptance of another deep paradox. Experiments in particular require time-persistent observers and apparatuses that interact while remaining separable in the physicist's sense of having independently characterizable states. Joint states of interacting systems are not, however, separable under unitary evolution prescribed by quantum theory. This paradox can be stated starkly. Local decoherence requires global coherence, that is, global entanglement. From a global theoretic perspective, both decoherence and the classical world it produces are epiphenomenal. Dietrich also points out that we have offered no theory of how human beings can formulate within their classical interfaces theories of the non-classical. This is a fair challenge that we hope someday to accept. Consciousness is fundamental, but architecture must be fundamental too. Both Dietrich and Urban Kodresch suggest that we are trying to explain phenomenal consciousness, or at any rate not taking it to be fundamental. We were perhaps not sufficiently clear that we take phenomenal consciousness to be fundamental and irreducible, and simply assume that conscious agents have it. However, we also assume that conscious agents have an architecture in addition to consciousness. The structure and content of phenomenal consciousness, that is experience, alone, we claim, insufficient to explain itself. E.g., sufficient to explain the structure and the content of the experience classical world. Kordesh specifically argues that our distinction between the experience space X and space G of available actions is a mistake. G, Kordesh suggests, should be a subset, presumably a proper one, of X. Being autonomous, he claims, means that the agent chooses from the options the agent itself constructs rather than from pre-given options. Placing G within X results, however, in an agent aware of every available action and of every choice of action. No action by such an agent can be automatic, as psychologists such as John Bargh and Tanya Chartrand use these terms. Genuine autonomy, moreover, requires that the agent be able to actually perform whatever action is chosen. This is possibly only if the world never interferes to prevent the chosen action. The conscious agent CA formalism separates G from X, not just to enable automaticity, but also to take the evident ability of the world to interfere with our desires into account. The best argument for the existence of a world independent of your own mind is, as the Rolling Stones explain it, you can't always get what you want. And we end there, and I thank you very much and wish you a pleasant morning.